Welcome everyone to the third and final part of our three-part webinar series exploring the latest enhancements in SigmaXL version 11. I'm your host, Paul Petrin, and I'm joined once again by John Noguera, co-founder and chief technology officer at SigmaXL. In today's session, John will guide us through fraction of design space, FDS plots, and introduce optimal designs, two valuable additions that further enhance the power and precision of SigmaXL. As always, we encourage your questions throughout the presentation. Just type them in to chat anytime, and we'll address them live during the Q&A portion at the end. Just a quick reminder, for product support and questions outside today's scope, you can reach our team at support@sigmaxl.com. If you missed any of our previous webinars, don't worry. Recordings, presentations, slides, samples, datasets, they're all available for download at sigmaxl.com. While you're visiting, be sure to explore our latest podcast series with the first AI-assisted episode on definitive screening designs. All right, let's dive in. John, over to you.
Thank you, Paul, and thank you all for your participation in our third and final webinar, What's New in SigmaXL version 11. Just a note, if you wish, you can connect with me on LinkedIn. This is my LinkedIn address. And so with that, we'll begin. Our agenda for today is we will discuss and introduce the fraction of design space plot and interpret the FDS plot. We'll use two examples, a one replicate cake bake response surface example, taste score to improve the cake taste quality with a single replicate, and then we'll do a double replicate and compare the two using FDS overlay plots. Briefly, we'll look at the differences between central composite rotatable, central composite faced, and a Box-Behnken design, again using the FDS plots. And then we'll switch gears to talk about optimal designs. First, we'll compare optimal to Factorial designs. We'll compare optimal to central composite response surface designs. Summary, when to use optimal designs, and then we'll talk about the differences between D-optimal, I-optimal, and A-optimal, and using the fraction of design space plot to assess these optimal designs. We'll talk about the design diagnostic metrics and the use of the model term standard error and variance inflation metrics, and an overview of what to use when for optimal designs. And then we'll conclude with an example of a constrained D-optimal design from Montgomery adhesive bond strength. And then we'll do Q&A. At the back of the presentation, we have the fraction of design space formula details and the optimal design diagnostic metrics and formulas and the references. These will not be covered, but I want to mention these to you that they are on the slides that are available for download for your reference. So let's start with the fraction of design space plot. So for two-level factorial and fractional factorials, power analysis is very useful to assist in design, determining number of replicates, and trying to determine how do you right size your factorial experiment to ensure that you are able to detect effects of interest. So that's the power analysis. Now, on the response surface designs, we have a similar tool called the fraction of design space plot. And this assists the practitioner to select and right size their response surface in optimal designs. This plot was introduced by Zahran, Anderson, Cook, and Myers, and it provides a visual representation of how well the design covers the experimental space and helps in assessing the precision of predictions that can be made from the design. You can use this in very practical ways, as I mentioned, for power, number of replicates, but you can experiment with replicates, you can experiment with number of center points, alpha axial value for central composite, whether you're going to use a central composite or a Box-Behnken, and the various optimality criteria. So it's really a very useful way of allowing you to compare different designs and giving you a picture of the prediction ability of that design before you collect any data. So that's the key here, right? Before you collect any data, you're able to assess the design quality using the FDS plot. So it shows the prediction standard error of the mean, and it shows the margin of error versus fraction of design space. So here's an example. We'll be looking at these in greater detail. On the x-axis is your fraction of design space from 0 to 1. On your y-axis is the standard error of the mean. This is the prediction standard error, and this is the margin of error. All right, so both are presented in the FDS plots, and we'll be looking at that in greater detail. When comparing FDS plots, lower is better and flatter is better over the majority of the design space. As I mentioned, it's produced prior to any data collection. So like the power calculations used in factorial designs, FDS assumes that the model standard deviation is 1. However, if you know the standard deviation, you simply multiply the FDS plot values by the standard deviation to get actual response units. All right, so you basically have either a standardized or actual, just depending on whether or not you know the process standard deviation. So if you know the process standard deviation, you can use the margin of error plot to assess if the actual prediction error will be acceptable over the majority of the design space. And typically for majority, we use anywhere from 80 to 95% as our guidelines. In this example, we'll be using 95%. We're saying 95% of the design space meets the required prediction margin of error. Note, a model must be specified for FDS, and typically that will be response surface quadratic model. So main effects, two-way interactions, and quadratic terms. And we typically will use a 95% confidence level. So the FDS plots are computed using Monte Carlo simulation. A uniform distribution is applied, and the values are coded from -1 to +1. This is known as a cuboidal. So even if the design is rotatable, we only simulate from -1 to +1. And the reason for that is because it allows you to compare. You can compare central composite and Box-Behnken. So it basically gives you more flexibility to compare across design types. And if you want further details, formula details are at the back of the PowerPoint as well as in the appendix of the SigmaXL workbook. So standard error of the mean and the margin of error are computed for 100,000 random values. This is all done very quickly in SigmaXL. They are sorted from smallest to largest, and the results are plotted as SE mean versus fraction of design space and margin of error or interval half width versus the fraction of design space. And we use 1,000 plot values to do that. Then we can do overlay FDS plots. After we've created multiple FDS plots, you can use overlay. And here we see the 1 replicate versus a 2 replicate. This is the cake bake example that we'll be using. So right away you can see that for a single replicate, you have much higher standard error of the mean and much higher margin of error interval half width. Okay, so you really get a lot from that second replicate. All right, again, we'll come back to that with the actual cake bake example. So in summary, the standard error of the mean and the margin of error, smaller is better, flatter is better over the majority of the design space. And you try to achieve this with minimum runs. If the process standard deviation is known, you multiply the SE mean and the margin of error by the standard deviation to estimate the actual prediction error versus the fraction of design space. Okay, so we're going to now jump into an example. This is the layer cake bake experiment revisited that we've seen before in the response surface examples. And the response variable is taste score on a scale of 1 to 7, where 1 is awful and 7 is delicious. Average scores for a panel of tasters have been recorded. The X factors are A, bake time, 20 to 40 minutes, and B, oven temperature, 350 to 400 degrees Fahrenheit. The experiment is a 10-run central composite design with 2 center points, face-centered with alpha axial equals 1.0. And what we're going to do is we're going to actually just go through, create the design, and manually look at the predicted response calculator. So if we were to do this manually, if we didn't have the FDS plot, we'll just kind of show you what steps would be involved and then how the FDS ties to this prediction error that is given in the predicted response calculator. All right, so with that, I'm going to switch over now to the menu. Let me just bring it up first. So SigmaXL Design of Experiments, Response Surface Designs. This is the cake bake example. So we want two factors. We have time and temperature, and we'll use a 10-run central composite design. The number of replicates is 1 for our first example. We want face-centered with alpha equals 1. I'm going to use a seed value of 1, 2 so that we have replicable results. And the fraction of design space plots are turned on. The factor A is time. And the low setting is 20 minutes. The high setting is 40 minutes. And the second factor, B, is temperature. And the low setting is 350. 350 to 400. The response is taste score, so we'll just type taste. And that gives us everything we need. And so this is a single replicate. The FDS is, as I mentioned, we'll use the response surface design as the model for the FDS plot. We go ahead and create the design. So you have your time and temperature settings randomized, ready to go out and bake cakes with these settings, and have your panel of tasters assign a score from 1 to 7. And note, however, that we haven't collected any data, and yet we're able to see the standard error of the mean over the fraction of design space and the margin of error over the 100,000 simulated runs with this particular design criteria, which is 10 runs. Central composite, alpha equals 1. So you have it right away. If you scroll down, and we'll come back to these, you have your percentiles given. So the number that we're going to be interested in is this 95th percentile for the standard error and the 95th percentile for the margin of error. So 1 point, basically 2.0 for the margin of error. And then we're going to multiply that by the historical standard deviation. Okay, so I'm going to come back to that. What I want to do is we have sample data that is already populated. So RSM FDS example 1, the taste scores have been populated, so we can just go ahead and analyze this data. And to do that, we go SigmaXL, design of experiments, response surface, analyze response surface, and we use the taste score. The default here is main effects plus two-way interactions plus quadratic. We'll select all. This is an RSM design, so we can estimate the main effects, the interaction, and the quadratic terms. I'll turn off residual plots for this, and we'll go ahead and run this. And this gives us our regression model. R squares are good. All the terms are statistically significant, which is good. So what I really want to do now is I want to look at the predicted response calculator. So what I'm going to do is I'm going to enter a value here of 30. So I get my standard error in my lower and upper confidence interval. So what the FDS plot gives us is, I'm going to say the upper minus the predicted value. This 0.42 is the margin of error. All right, so this is the standard error right here, and upper 95 minus the predicted response, that is the margin of error, or the half interval half width. And now, because we're measuring from on a scale of 1 to 7, this is actually pretty high. This margin of error, a 0.4, compared to your 1 to 7 scale, is really higher than you would like. You know, you're saying it's basically almost half a unit in prediction uncertainty. So that's pretty high. Now, we didn't have to do any multiplying because this is the regression model with the data. All right, so you have your standard deviation of 0.25 and so forth. And whenever you actually have data, of course, you can just go ahead and analyze the data and do your predicted response calculator. But what the FDS plot does is it gives you, before you collect any data, the ability to assess your prediction uncertainty. Let me just change some numbers here. So let me scroll over back to the calculated value, and I'm going to change the input from 30, I'm going to change it to 20 and to 350. Just a couple of different random values in the time temperature settings, and now we have an even higher margin of error, or half interval, of 0.62. All right, so what the FDS does is what we've just done manually does it 100,000 times. Okay, so effectively, like, think of it as just taking this predicted response calculator and randomly assigning time and temperature values and doing that 100,000 times, recording the SE and recording the margin of error, sorting it from smallest to largest, and then plotting it on the SE mean versus fraction of design space and the margin of error versus fraction of design space. All right, let me go back to the PowerPoint here. The fraction of design space plot repeats this process 100,000 times using a uniform random number from 20 to 40 for time and 350 to 400 for temperature to obtain 100,000 SE and half interval values. These are sorted from smallest to largest, and the results are plotted as SE mean versus fraction of design space and margin of error versus fraction of design space using 1,000 plot points. You can hover the mouse cursor on the FDS plot to obtain values for any fraction of design space. Again, smaller is better and flatter is better over the majority of the design space. That's what you're looking for, smaller and flatter. You also have the summary statistics, all right? So that's what I had briefly alluded to it. And in the summary statistics, the number that we're going to use is this 95th percentile. So here we can see that the standard error of the mean for the 95th percentile can be as large as 0.72, and the 95th percentile 1.99 for the margin of error. Now, to obtain units of taste score, we multiply the model standard deviation. We multiply the SE mean by the model standard deviation. In this case, it's 0.25, so we have an SE mean of 0.18 and a half width of 0.5. All right, so this is quite large, again, because we're on a 1 to 7 scale. Just a point of clarification, note that the confidence level of 95% applies to the margin of error. The 95th percentile applies to the fraction or proportion of design space. Don't confuse these two. These are two different and distinct things. Since these percentiles are based on Monte Carlo simulation, slightly different results will be observed every time they're produced unless the fixed seed is used. So we're now ready to switch over to two replicates. All right, so let me go back here and just go here, response surface designs, number of factors is 2. I changed the number of replicates to 2. I can block on replicates, face centered, again, set the seed to 1, 2. And, to save time, I'm not going to populate the time and temperature and taste. I'll just run this because we're going to use a pre-populated worksheet anyway. So you just click OK, and that gives you your new FDS plot. Now, it's kind of hard to actually compare the FDS just standalone. Where it's going to come really handy is when we do the overlay plot. We can, again, look at the percentiles, and we already see that these numbers are quite a bit lower than the single replicate case. Before we do that, let me just actually run with the pre-populated example. I'm going to analyze this. So design of experiments, response surface, analyze response surface design. So again, I'm doing the RSM. And I'm going to do the same thing that I did before with the predicted response calculator, and I'll enter 30. My margin of error is my upper. By the way, you don't have, this is something you won't need to do when you're using your FDS plot. I'm only doing this to illustrate what the FDS plot is doing. So notice our margin of error is quite a bit smaller. All right, so that's a significant reduction in margin of error. Let's bring up the slides here. All right, the margin of error is 0.18, a dramatic reduction from the previous value of 0.42, and is an acceptable interval for the 1 to 7 taste score. So rather than 0.42, it's now 0.18. So that's going from 1 replicate to 2 replicates has really made a dramatic improvement in the prediction precision. However, again, the FDS plot would do the same thing 100,000 times. All right? So that's really what we want to emphasize here, is that the FDS plot can now be used to compare between the single replicate and the double replicate case. So the way we do that is we go to Design of Experiments, Overlay FDS Plots, and so example 1, example 2, I'll label example 1 as 1 rep, and I'll label example 2 as 2 replicates. And now we can immediately see that in the single replicate case, we have much larger standard error of the mean over the fraction of design space from 0 to 1, over the 100,000 simulated runs of the predicted response calculator. And we can again compare. So the overlay FDS plot allows you to make that comparison. And in this particular case, after we multiply by the process standard deviation, we can now say that the 2 replicates gets us where we want to be in terms of prediction error. All right, so that's what I wanted to do by way of introduction to FDS. And let me just go back to the PowerPoint slides and move on from the cake bake, 1 replicate versus 2 replicates, to the comparison of different RSM design types. So to save time, I'm only going to just do the PowerPoint portion here. We'll compare a central composite rotatable design, which has 5 levels, to a central composite face-centered design, which has 3 levels. Alpha is 1, and a Box-Behnken design. Graphically, you can compare the 3 designs. The CCD rotatable design is like a sphere, spherical. The central composite face design is cuboidal. And the Box-Behnken design is also a 3-level design, but you'll notice that it does not have values out at the extreme Q points. And that could be an advantage if you wanted to avoid, for example, max conditions for your design. So the Box-Behnken may be useful for particular cases where you want to avoid actually having to collect data in the extremities. But in terms of how the performance looks from a prediction precision point of view, you can see the Box-Behnken has much larger standard error of the mean because of the absence of data points in the cube corners. Whereas the central composite rotatable has this nice flat, this is uniform precision design, so nice flat FDS plot. And that's one of the reasons why it's highly desirable to use a rotatable design, but that assumes you can afford the runs, and that assumes that you can do the 5-level design. So, for example, it might be a good compromise to use the central composite faced. So that's the orange design. And actually, the central composite face does quite well for the first 60% of the designs. And then for the 40%, rotatable does better. So remember, lower is better, flatter is better. So for this portion of the design space, the rotatable is better. And for this portion of the design space, the face is better. Lower is better and flatter is better. But for sure, unless you actually have a practical requirement to avoid those extremities, I would not recommend using the Box-Behnken design, just based on the fact that your prediction error is so much bigger in this portion of the design space as you approach these corners where you don't actually have data. Okay, that's it for response surface. Now what I want to do is switch gears, and I want to talk about optimal designs. So we'll come back to fraction of design space, but now we're going to talk about optimal designs. And I want to compare optimal designs to classical factorial designs. So factorial and fractional factorial designs have ideal optimality statistics. They're orthogonal. They have a clearly defined alias structure, and they're easy to understand, relatively easy to understand. So if you just need to do a basic DOE, then use a factorial or fractional factorial design. You don't need an optimal design just because it's a cool design to use. Categorical factors for factorial designs are limited to 2 levels. You can get more levels with the general factorial, but that quickly explodes in the number of runs. Also, factorial designs cannot accommodate factor constraints. Finally, optimal designs are more efficient than factorial designs, so if your runs are expensive, then the optimal may be a better choice here than a factorial design. So now comparing optimal designs to response surface designs, central composite response surface. Central composite has really nice statistical properties, rotatable, that is, it has the same prediction variance at all points that are the same distance radius from the center of the design, regardless of direction. Uniform precision, nearly flat FDS, we saw that on the FDS plots. And they're close to I-optimal, which means that they have very good prediction error properties. All right. Categorical factors are permitted, but the RSM design is replicated for each level combination, so that quickly explodes in the number of runs. Also, RSM designs cannot accommodate factor constraints, so optimal designs are more efficient than RSM designs. So in summary, when would you use an optimal design? 1, if you have linear factor constraints. Then you really have no choice. You have to use an optimal design. You have a mix of continuous and multi-level categorical factors, and if the number of levels or the number of categorical factors is large, then that quickly blows up on you, so you want to have a more efficient design, then an optimal design would make sense. In general, if the runs are expensive or difficult and you need the most efficient design possible, use an optimal design. Also, if you have a model that where you're not really you're interested in something different from a straightforward quadratic RSM model or fit, maybe you want to estimate a quadratic term only for specific factors, or you want to estimate cubic terms. All right, so the optimal designs give you that flexibility for a custom model. And then also, if you have an existing design and you want to augment it, then optimal can be used. Currently, we don't have that. That is coming in 11.1, augment optimal. But that's another use case for optimal. All right, so de-optimal designs. A de-optimal design maximizes the determinant of the information matrix, which minimizes the volume of the joint confidence region of the estimated regression coefficients. This results in good overall model precision, so is recommended as a general purpose alternative to screening and 2-level factorial designs. So de-optimal, general purpose alternative, and using a very simple slope and intercept model, we can see here this is the uncertainty, and this would be a non-de-optimal design, and this shows you the de-optimal design. So the de-optimal designs are especially useful when we care about the overall precision of all model coefficients together rather than any single coefficient in isolation. All right, so that's the de-optimal. And the computer does all the hard stuff. It's going to find the conditions, the runs that are going to best satisfy to maximize the determinant of the information matrix. And here's what happens in a simple case of 2-factor with a main effects plus 2-way interaction plus quadratic model. 6 additional runs are given for a total number of runs equals 12. And so the de-optimal picked the 9 points, so it's a 3-level design. plus it assigned a replicate here, a replicate here, and a replicate here. So it's using the corner points to get better estimates of the regression coefficients. All right, so that's what happened here in this de-optimal design. So now let's switch over to I-optimal. I-optimal design minimizes the average prediction variance or the integrated variance over the design space, which can be thought of as minimizing the area under the fraction of design space plot. And since the primary objective of a response surface design is accurate prediction and optimization, I-optimality is recommended for RSM designs. All right, so we have further details on the formulas in the appendices, and there's a good book on optimal designs by Goose and Jones that is referenced here. Now, what does an I-optimal design look like? Well, again, we start with the same 9 points, but this time we replicated the center points. So we have now 4 replicates at the center point, and that produces the I-optimal design. All right, so now you have single replicates out at the corners, but you've added replicates to the center point, and that improves the I-optimality. Now, A-optimal minimizes the average variance of the estimated regression coefficient terms. Now, recently, Jones came out with a paper recommending A-optimal for screening designs. And in that paper, they point out that A-optimality is more consistent with the screening objective. So what they're saying is that if you're doing a screening design, rather than a de-optimal design, use an A-optimal. The goal of the screening experiment is to identify an active subset of the factors. An A-optimal design minimizes the average variance of the parameter estimates, and that's directly related to the goal of screening. And while there are many cases where A and D-optimal designs coincide, the A-optimal designs tend to have better statistical properties when the A and D-optimal designs differ. In such cases, A-optimal designs generally have more uncorrelated terms in their model matrices than D-optimal designs. You can also get lower worst-case prediction variance when you compare A versus D. Now, one thing I want to say is it's really easy to generate, in this case, if you're doing a screening and you're not sure which one, you can do both because you're not collecting any data. You're just generating the design, and then you can look at the FDS plots, you can look at the metrics, and then make your decision as to what design type. We're just kind of giving the lay of the land here of the 3 different optimality. D-optimal is very popular, and in fact, we're going to use it in the Montgomery constrained example, but just keep that in mind, that sometimes A is better than D, and sometimes it's really not that much of a difference, all right? So practically, they both give very similar results. Here's what happens with this same settings. So what A-optimal did was put 3 replicates at the center point and then added 1 at the edge, all right? So that produced the A-optimal design. And looking at the fraction of design space plot, you can see that I-optimal and A-optimal are actually very, very similar, but the D-optimal has a larger standard error of the mean. Okay, so now we can look at optimal design diagnostic metrics. There's a bunch of them, and I'm just going to cover this briefly and focus on the most important metrics. So you have D-optimality, which you want to maximize. D-efficiency, where you would like 100 as your goal. The max is 100. The determinant of the inverse X transpose X, you want to minimize that. A-optimality is the trace of the inverse. You want to minimize that. A-efficiency, your goal is 100. Maximum prediction variance, you want to minimize. G-efficiency, you want to maximize. These efficiency scores make it really easy to interpret because it's on a 0 to 100. It's like R-square. It's not the same as R-square, but your interpretation. And sometimes these numbers can be really, really small, so they're not very practical to look at the determinant of the inverse to decide the quality of your design. And whereas the D-efficiency is D-efficiency, A-efficiency, and G-efficiency are much easier to interpret. I-optimality is your average prediction variance, and you want to minimize that. And your condition number, again, you want to minimize that. So D, A, and G efficiency metrics compare the efficiency of the design to that of an ideal orthogonal design in terms of the respective optimality criteria. A full or fractional factorial design without center points would have D efficiency, A efficiency, and G efficiency equal to 100%. The efficiency metrics are easier to interpret than the optimality metrics since they are scaled from 0 to 100. But unlike R-squared rules of thumb, you can't really say that a particular value is good or bad for D and A efficiency. So they're really used to compare designs, right? So you compare, for the same number of runs, I can compare two designs, and the one with the higher efficiency is the better design. But that's not the case for G efficiency. We do have a rule of thumb. Maximum prediction variance and G efficiency are calculated using Monte Carlo sampling with 1 million replicates. So you might get some slight difference for the same design. And Montgomery gives a rule of thumb that a G efficiency of around 50% or higher is desired, and standard response surface designs in regularly shaped regions typically have G efficiencies well above 50% and often in the 70 to 90% range. So this one is kind of like R-square. The G efficiency then becomes a very useful measure to use. A condition number, less than 100. More than 100 is moderate multicollinearity. More than 1,000 is really bad. So you're looking for multicollinearity less than 100. And then model term SE, variance inflation, and tolerance are also given. The rule of thumb, VIF less than 5. And the standard errors, obviously, smaller is better. And this is, again, just one slide putting together the optimal design diagnostic metrics for the D-optimal, I-optimal, and A-optimal. In each case, the D efficiency is the highest for the D-optimal. The I-optimality, we don't have an efficiency score for I-optimality, just the I-optimality variance is minimum for I-optimal, and the A efficiency is the highest for the A-optimal design. That's expected. But what's interesting is that the A-optimal design actually has the lowest condition number. All right, so in this particular case, of these three choices, I would go with the A-optimal design. It has the lowest condition number, and they are, in terms of, they're quite similar in terms of the other characteristics. The G efficiency is another one. Actually, the G efficiency for the A-optimal is the largest. So we have 63.0, 63.2, and 63.4. Now, mind you, these are small numbers, but it just gives you an idea of what to look for. So again, use your A efficiency and D efficiency to compare one against another. Use your G efficiency as your overall, that's the maximum prediction variance. You can use that one. It should be over 50%. And I optimality, lower is better. And then you can use this in conjunction with the fraction of design space plots. We also produce the standard errors. Again, keep in mind, this is all without data. You haven't collected any data. You're only produced the design, and you're still able to look at your model SEs, assuming a standard deviation of 1. So you could take the average, the RMSE, and in this particular case, the A-optimal has the lowest RMSE and also has the lowest maximum VIF. So that also relates to the condition number, and A-optimal in this particular case had the lowest condition number. So that is not to say that you should always use an A-optimal design over a D-optimal design, because there can easily be cases where D-optimal would be preferred over A-optimal, but what we're saying is at least try them out and then compare. One of the nice things about A-optimal is that it is more intuitive than a D-optimal. A-optimal minimizes the average variance of the estimated regression coefficients. All right, so hence is recommended for screening designs. Also, if you're doing a response surface design, I-optimal is generally recommended. Again, we'll leave D-optimal as a kind of general purpose optimal design that can be used, and use these design metrics, optimal design metrics, the standard error, the variance inflation factor, and the FDS plots in advance to assess what design choice you will pick. So it's very easy, very fast to try the different designs and see what you get. look, if you don't know which one to use, if you're doing RSM, you can use iOptimal. If you're not sure, you can use a D-optimal, mainly because people are more familiar with D-optimal. So that's, it's kind of 6 of one, half a dozen of the other. So let's go now to an example with the adhesive bond strength. This comes from a paper from Montgomery called Experimental Designs for Constrained Regions in Quality Engineering. An experimenter is investigating the bond strength of a particular adhesive. The adhesive is applied to 2 parts and then the assembly cured at an elevated temperature. The 2 factors of interest are the amount of adhesive applied and the cure temperature. Over the ranges of these factors taken from -1 to +1, we're using coded here just to keep it simple. The experimenter knows that if too little adhesive is applied and the cure temperature is too low, the parts will not bond satisfactorily. Furthermore, if the temperature is too high and too much adhesive is applied, either the parts will be damaged by stress or an inadequate bond will result. So because of this, we have 2 linear constraint formulas. A plus B must be greater than or equal to -0.5, and A plus B must be less than or equal to 1. The expected range of bond strength values is approximately 1 to 4, and for demonstration purposes, we will assume a process historical standard deviation of 0.1. All right, so I'm going to switch over now to run this. And design of experiments, optimal designs. We have 2 factors, 6 additional runs to support the model. We're going to use D-optimal. We're going to specify, actually, let me type in adhesive and temp. And the response is strength. We're going to specify a linear constraint. For that, we just type in A plus B is less than or equal to 1, and you use a semicolon delimiter. A plus B is greater than or equal to -0.5. All right? You always want to do a sanity check and make sure your linear constraints are specified correctly. And this only applies to continuous factors. All right? SigmaXL does not support constraints on categorical factors. The other thing that I want to mention here are the Madako settings. I mentioned the use of the mixed integer distributed ant colony optimization is how we solve the optimality criteria. And I'm going to increase this to, it's actually 1 million function evaluations with no change. Because when you're dealing with constraints, it's a more complex problem. I also want to point out that right now in version 11, iOptimality is grayed out. In version 11.1, we put it back in, so iOptimality will support continuous linear constraints in version 11.1. Again, we can set the seed value to 1, 2, and we'll turn the fraction of design space plot on, and then we can go ahead. We want the response surface design. And so that's our design. So actually, let's start with, so we entered the A and the B, but it actually puts it in as adhesive and temp so that you have a clear picture of what the constraints are. And if you want to manually check the constraints, you can actually just simply go in here and do a sum of adhesive plus temp and then that way you can just kind of do a quick check and you can see that yes, indeed, we are satisfying the constraint that the sum must be less than or equal to 1 and greater than or equal to -0.5. Another thing you could do here is you can actually create a scatter plot. So if we go to just to insert and we do an Excel scatter plot, you can actually now see the design space. You can see the upper right-hand corner and the lower left-hand corner. There's no data there because we specified these linear constraints. We can look at the design. So a few points here. The D-efficiency is on the low side, but again, as I mentioned, this can't be interpreted as bad. It just says that for the given constraints, this is the best we could do. And the G efficiency is pretty good, 74.4. That looks good. The condition number is 56. So that's, again, on the high side, still less than 100. So not bad. VIF, we have one at 11.8, which is higher than the 5 that we would like. All of these VIFs are on the high side, but that's a trade-off when you have, this is not an orthogonal design. So in order to satisfy your linear constraints, you have to sacrifice on some of these design properties. And in terms of the FDS plot, I'm just going to point out here that if we go to the 95th percentile, 1.66, so we multiply by 0.1, 0.16 on a 1 to 4 scale, that's good. So we're based on our FDS plot multiplied by our historical standard deviation, we're predicting that the margin of error is going to be satisfactory over the majority of the design space. All right, so that was this 95th percentile. 1.7 times 0.1 is 0.17, and we had that, we're using a 1 to 4 scale, so that's an acceptable uncertainty for prediction purposes. Again, we haven't actually collected any data, so let's go off and let's collect our data and open up the pre-populated worksheet, which has the strength values applied. The one thing that, in addition to doing a scatter plot of the factors, we also show the candidate reps, and the workbook kind of shows you how in Excel you can add labels to your plot points to indicate where the replications are. So I'm not going to do that here in this demonstration, but that's just a straightforward use of Excel, straight Excel functionality. What I want to do is I want to now analyze this data. So we'll go SigmaXL, design of experiments, optimal, analyze optimal design. We want a response surface design. We want strength as our response. We want a response surface design. Click OK. So we got good R squares, high R squares, everything is statistically significant. The residuals look good, no obvious patterns. And now we want to go to the predicted response calculator. Let me just put in 0, 0. And if we do the upper minus the predicted, that gives us our margin of error here, which is 0.14. And that's pretty close to what we were seeing with the FDS plot. Remember, the FDS was done before any data was collected. So what I want to do now is I want to maximize. I set my goal and I run optimize. So find the maximum settings to maximize my adhesive strength. This takes a bit longer because it is optimizing with the constraints in mind. Those linear constraints are being considered in this optimization, so the optimization procedure takes a bit longer. So the predicted response is 4.04, which is what we wanted to go ahead and predict. And there's our settings for our predicted response. Okay, so that actually concludes my presentation. And I know we were kind of sorry for rushing through some of this, but we can now open it up to any questions.
Thank you, John. So we are now down to the Q&A portion of the webinar. Actually, John, there is a question here that I have for you. Can you provide a short answer to how the FDS calculates the SE, et cetera, with no data to fit the model? What does it assume or simulate exactly?
Okay, well, let me just pull up. So I don't want to go into too much detail here, but the first thing is you're assuming a standard deviation of 1. The variance term is assumed to be 1. All right, and that's why if you know the process standard deviation, you can simply multiply it by the SE term that you get in your FTS plot. This is basically the x transpose x, and we're solving this, which is the regression equation. Think of it as we're solving the regression equation over 100,000 different conditions for possible input values from -1 to +1. Also, if it's categorical, you can actually do the same. It's going to apply random numbers to the integer distribution for categorical. So once you solve your standard error of the mean, you have 100,000 values, you sort it. Then to get the margin of error, you just apply the t-statistic as a multiplier to get the margin of error. All right, this is actually the same formulas that are used in the prediction regression equation, only you're able to solve it without data because notice there's no y term in this equation. All right, in order to get your actual standard deviation, you clearly have to have data, or historical data. Just like power, remember with power, you're doing power calculations, you assume a standard deviation of 1 in order to estimate effect size in units of standard deviation. So it's the same concept.
Can you please explain why the CCD face-centered model is better for the first 60%, but the rotatable design is better for the next 40%? I see it on the graph, but I'm confused why this curiosity occurs.
It's a good question. So first of all, we're only looking at the cuboidal space, right? We're not actually in the FDS plot. We're not going out here into this region. We're staying within the cube. So if you think about it, because these points are right on the edge, that's improving the prediction error. You're actually having data right on the edge. The disadvantage is that it's not as flat. You don't have that uniformity and you don't have the rotatability. But yeah, so you do have nicer, at least in 60% of the design space, the face center does better than the rotatable design. But one could argue the fact that it's flat is a strong case for a rotatable design.
Is there any way to add a constraint to VIF?
No, it's a straight linear constraint on the prediction factors themselves, and the VIF is an outcome. So you would have to basically apply the constraints and then look at the condition number and look at the VIF scores. But there's no way to specify that, optimize it subject to the condition of a maximum VIF. I guess that's something that could be done, but certainly not in the software that would allow you to maximize the optimality subject to a VIF constraint.
There's another one that just came in here. General question, where can the DOE be applied to processes in hospital operations?
I'm not sure if this is just DOE in general or what the topic we've covered, but let's say, I'm assuming the question relates to optimal designs. So if in hospitals, one of the things you have are it might take a long time to collect data. So it may not be expensive, but maybe the response time, rare events or something like that takes a long time to collect data, then an optimal design would be very attractive because it's very efficient. So as long as you have controllable factors, you have inputs that can be varied and randomized, then you can apply a DOE. And in particular, those cases where it's hard to collect the data or expensive, then you would want to use an optimal design.
That brings us to the conclusion of our 3-part webinar series on the new features in SigmaXL version 11. We hope today's session and the series as a whole has given you valuable insights into the powerful capabilities of SigmaXL and inspired you to explore what's possible in your own analysis and designs. Your questions, feedback, and engagement are what make these sessions so rewarding. As always, we welcome your thoughts and encourage you to continue your conversations with us. Today's presentation materials, including the PowerPoint slides and example datasets, they'll all be available for download on our website. A recording of this session will also be shared soon. On behalf of the entire SigmaXL team, thank you for joining us. It's been a pleasure having you along for this journey. Take care and enjoy the rest of your day.
Thank you all. Thank you for your participation.